Now today class we are going to talk about the next chiral molecule with no stereogenic centers. Okay. So the molecule which we are going to discuss today is called as biphenyl type. Okay. And this biphenyl type molecules, they also exhibit, we call them as a atrope isomerism. We call that process as a atrope isomer, these two isomer, but still we can call them as an isomer. This is happens because you look this structure will tell what you look into this. One phenyl ring will be in the plane with two substituent. Another phenyl ring will be perpendicular to that with two phenyl rings away from this phenyl ring. Okay. So because you have this rotation here possible, okay, this happens to get away from these two substituents. For example, if you take this carboxylic acid and this carboxylic acid, there will be a very good steric repulsion. And this nitro and this nitro will have a very good steric repulsion. To avoid this steric repulsion, there's a sort of bond rotation happens here, CC bond rotation, so that one phenyl ring ends up in the plane, another phenyl ring will be perpendicular to that or orthogonal to that, so that you have four substituents in different, two substituents on plane like allene and two substituents, one towards the slide and one substituent away from the slide. So this also exhibits stereo optical activity, and we call this process as atropia isomerism, or we can call them atrope isomer. Okay. So now I want to teach this in detail. Okay, just to show the molecule. Now shall we go in detail and look into that, how it exists. So stop sharing. I'll take another PowerPoint because this PowerPoint I wanted to use for your clarification, double clarification. Okay. So this will be the right way. Okay, fine. Okay. Okay, now we'll take the biphenyl compound. Now I told how this biphenyl exists. Okay, you take this simple biphenyl. You can see my drawing, right?
Yes, sir.
Okay, fine.
Yes, sir.
This biphenyl always have this habit of rotating here because you know that it is a single bond. So this CC rotation happens nicely and very fast. Okay. Now you leave this part. Now we'll start with first type of the one, which is mono. Okay, mono substituted. I'm taking a biphenyl. I'm making a mono substituted of this. So the first rule, I am going to check the optical activity. So we are trying to formulate a rule. Okay. Okay. So I have a nitro compound here. You think this molecule exhibits chirality, or this molecule has optical activity, exhibits optical activity?
No, no, sir.
No. Why?
Sir, because both the groups are same in the left side by phenyl ring.
So you are saying me one thing is that, sir, as you are taught me in the class, that's the first rule is trying me is correlating with allene. That's the best way to go ahead. He says that, sir, as you teach me in the class, A should not be equal to B and C should not equal to D. But in this case, A and B are same. Very good. That's one of the reasons. Okay, fine.
Now it is also in the same.
It's also in the same plane.
Same plane.
Very good, very good. So the second rule, I thought I will teach one by one. Anyhow, you guys are too good. So it is also in the same plane and it is rotating very fast. That also I can say, okay? It rotates very fast that even if it exists, I cannot separate them out. It doesn't exist, that is first case, okay? Okay, now come to the bi case, bi-substituted, biphenyl. We'll take a bi-substituted biphenyl. So if there is a mono-substituted biphenyl, don't worry about its optical activity. Immediately you can say, sir, the given compound is not optical active. We will ask you, we will give you 5-6 biphenyls and we'll ask you to select the biphenyl which is optically active. Okay? If you have a mono-substituted, immediately you can say that it is not optically active. Okay. Now come to the bi-substituted. For example, I have a carboxylic acid. Carboxylic acid. Is this compound is chiral or this compound is not chiral? Or it's a chiral or optical activity that is affected?
No, sir, not chiral.
Not chiral, sir.
Center of
Because,
symmetry.
Yes, sir, no.
because my first rule, A is not equal to B and C is not equal to D, right? This is right with this. Fine. It
Yes,
obeys
sir.
with the first rule, but where it loses is chirality. Why it is not chiral?
The center of symmetry.
Center of symmetry 1 or plane of symmetry, center of symmetry, very good. Then any other reason?
Sir, planar.
Sir, meso
So
compound.
here rotation is log, so same thing.
Yes, sir.
So I can then take the symmetry word, right? Because of that, it is not chiral. So this is achiral finally, and this is also achiral. See, I am trying to, so that you will get no problem in finding out the chiral molecules. If it is bi, so mono and bi, you are directly going to write that it is not optically active. See, most of the time we don't ask reason, but still it's better to know the reasons also. Okay?
Sir, if it was bi and the two substituents were different,
No, no,
what would
that,
that be?
yeah, that's why I am with bi. Okay?
Oh, okay.
Huh?
Excuse me, sir.
Yes.
Sir, here both the biphenyls are in same plane or in perpendicular planes.
No, but see, basically the idea is that, as you asked, is very important. Now, since it is a two substituents, right? So this will keep on rotating. Even if you keep it in the perpendicular plane also, these two molecules will racemize very fast. So you cannot differentiate them. Okay? This will be keep on rotating very fast. Fine?
Yes, sir.
Okay. That is, I think that I wanted to bring in the third thing, but you asked more important. That's good. Okay. When I use this tri system, I think I will answer your question more easily in the tri substituted system. You take a tri substituted system. Fine. So I can have different things here. Nitro. I can have a chlorine. I can have a nitro and hydrogen. Okay. This is tri-substituted. Now let me know what happens here. Is this chiral or this is not chiral?
Sir, this is chiral.
Iron.
So why you are afraid to say that? See, if you are not confident, then things goes very wrong. Then
Sir,
it is
actually,
like,
there are some rules regarding the sizes
yeah,
of the
very good.
substituents. So
If it is
we do
A is
remember
not equal to B, 1, C is not equal to D, so it exactly finds out. And the second rule is that there is no symmetry exists here. No symmetry. Very good. Fine. Now, the third thing which is very important, I have to fix a rule here. The third one. This is only makes a difference here. Okay. That's why I wanted to bring the third rule in this case. For example, you have a system like this. We say that the system is chiral, okay? Because it is tri-substituted system, we say, sir, it should be chiral. I accept that. For example, if I draw a system like this, nitro, fluorine, hydrogen, and I have a fluorine. Okay, I can have a here deuterium. What? Deuterium. This is deuterium. Okay. Now you tell this is tri-substituted system, right? See, tri-substituted system only you should be careful. Mono bi, the chirality of biphenyl never exists. Okay, you can directly say no to it. No need to worry about anything. When you come to tri, you should be really careful. Okay, tri-substituted systems. Okay, tri-substituted system is this system is chiral or not?
The second one is not chiral.
Sir, no.
Yes,
So
second one is chiral.
if I look my rule, A is not equal to B, C is not equal to D. Second, no symmetry. It should be chiral. Why it is not chiral?
Sir, A and D are not steric enough, so it is
Huh?
not.
So the steric hindrances matter. So there could be rotation about the single bond.
Now that's why I brought the concept of third rule, that is the rotation. Okay, what? Rotation of this molecule. This rotation is very important. So basically, if the molecule rotates, what will happen? But the molecule can racemize. They can be in two different compounds, but still it is rotating. I cannot separate them out. They racemize very fast. So the given molecule can be taken as a chiral molecule. Okay. So now the condition comes, yes sir, for tri-substituted, I have to look into the third rule, which is very important, that is rotation. So how to understand this rotation, sir? So the basic idea to understand rotation is that if we have small substituents, so what I mean by small substituents, okay, can I write R for small substituent? Huh? If I have small substituents like hydrogen, deuterium, tritium, and fluorine, there will be definitely rotation taking place. This was in previous year JAM question paper. Okay, fluorine, they gave fluorine. Still, people thought it is tri-substituted and said that it is optically active. And they went and R and S and they found it is enantiomer. Completely wrong. So till fluorine, you can say that this will rotate. There will be no steric. Okay, this steric will be less. That's why I call small substituent. I can say that steric will be less. So if you go for a bulky groups, so what are the bulky groups with respect to biphenyl? So I can say CH3, you can have chlorine, bromine, iodine, then you can have carboxylic acid, SO3H, okay, and even you can have nitro groups. So these are all will make the compound bulky in nature. So then you can say, yes sir, this can be a steric repulsion and the CC rotation will not be free and I exhibit chirality, the molecule exhibits chirality. But if you have this four substituents like deuterium, tritium, fluorine, hydrogen, you should be really careful. Clear, sir?
So the bulkiness
Sir,
increases
carboxylic
towards the
acid.
right, right?
Huh?
Yes, sir. That order should be reversed, I think.
Yeah.
Bulky.
Okay, sorry. I'm really sorry. I should have not used this. I have not used this. Sorry. I should have used comma. Because I'm saying all the groups. These are the groups. Once you find, you should be. Okay. It's not great.
Basically,
essence.
means,
Yes, sir.
sir, in a small group rotation is too fast to separate the molecule so that it
Yeah.
is achiral.
Yeah. So if you see for exam point of view, yes, you will be writing this as achiral. But a research point of view, I can tell you that this is we are talking with respect to room temperature. But once we go to the lower temperature, even with the fluorine system, we can isolate these guys. We can stop them racemizing, and we can able to isolate these guys and keep it in the at minus 10 degrees Celsius or minus 40 degrees Celsius. Okay,
So
still they can be
that
separable.
means
And
eventually.
room
So
temperature
that
we are
means.
talking. Yes.
So that means even for chiral molecules, even if we increase the temperature eventually, and
Not
suppose the
increase,
chemical
decrease the
reaction.
decrease the
No, sir,
temperature.
I'm just saying the opposite. If it happens for
Uh,
chiral molecules,
uh.
then eventually they will become achiral because of rotation increasing.
Yeah, definitely. When you heat the reaction, that's what dynamic stereochemistry we were talking. Okay, that's how the stereochemistry completely changes from R to S. Molecule becomes chiral to achiral. So we are talking a static stereochemistry at room temperature. That is very important. What you said is also completely right. Uh, If you go
Okay,
towards
sir.
lower temperature, you can racemize the mixture, you can separate them. If you go towards higher temperature, you end up in getting more racemization also. Okay, nothing.
Okay, sir.
So,
Excuse
Sir,
me, sir.
basically,
yes,
we can
sir.
separate enantiomers, then we can say it is chiral. If we cannot separate enantiomers, then we cannot say it is chiral.
What separate means? What you are talking? Yeah, separate at the room temperature. If at least we can visualize them. It's not
Yes, sir.
even
If
to
we can,
separate. If you can even visualize them, it's more. It's enough at room temperature.
Excuse me, sir.
Yeah.
Sir, when the light passes through the polarimeter at one instant, then even if rotation is happening, the light will rotate, no?
Yeah.
Because the molecule is asymmetric.
Hmm.
But we are just saying it's occur because we are not able to separate the
No, even the
enantiomers.
light, for example, if you are doing an optical activity at a room temperature, this rotation will be very fast that the light cannot see that.
sir,
It will see in both the
sir,
mixtures.
also this will
But
be
if you do the optical
mixture.
activity,
So,
I think can I answer one by one? It will be really nice. Then there will be cross talks. Then I cannot answer any one questions. Okay. If it
Sir,
is
but
one by
when
one, very good. I have a lot of time. Don't worry. So I will finish this optical activity question. So if I take it in the ice mixture and keep it in the optical activity, we can definitely see them different lights. See, you have an anosomeric excess will be considered. Okay.
Sir,
Mm.
Dr. Sir.
Yeah.
Yes, sir. Sir, in the second question, in the second part, when it is pi substituted, then sir, the symmetry is plane of symmetry or center of symmetry?
Don't worry of the. I will be always bifinal. I will look for plane of symmetry most of the time.
No, yes, sir. But in the bi substituted part, means in the second column, that symmetry, that's plane of
Which
symmetry
symmetry?
or
Yeah.
plane of.
Plane of symmetry.
So not in the tri one, the bi one.
Yeah.
That's
This
how.
is plane of symmetry. You can make it. Okay.
Okay, sir. So this will not rotate actually.
Yeah. This will rotate. Definitely, this will rotate. But plane of symmetry is also there. Its rotation will be very slow. Okay. Once these two carboxylic acid meet there, they will repel and they will rotate back. Rotation is there, not that great. Okay. But plane of symmetry is meant.
Plane of symmetry.
Sir, both won't be in the same plane now, sir.
Yeah. But it doesn't mean that. See, these molecules are static at room temperature. That's why these molecules doesn't stay like this all the time as you think. Okay, they will always flux. Okay. You think this molecule will be sitting like that all the time? No, they will always rotate. Then once these two carboxylic acid meet each other, then they will come back. Then they will come again. They will turn around, come to two carboxylic acid meets again. Then again they will come back like that. Okay.
Sir, if the second carboxylic acid it rotates and stays in the 90-degree angle, then sir, it can stay, right?
It will not freeze out. Okay. Molecules doesn't freeze out. Okay.
Okay, got it.
Yeah. Freezing is not possible at that molecule. All the molecules fluctuate, they rotate, they do everything. Okay. But we can always say that this is the minimum energy conformer. Okay. Where it exists in the highest probability. That's all you can say at a given time.
Sir,
Okay.
so all these molecules will like have some energy for rotation, like energy barrier. After which it will rotate.
Yeah.
So like these molecules that have larger groups, like more steady groups, will have higher energy of rotation. Just that, right?
Yes, yes. So that's
So
what
at
I'm
room
saying.
temperature,
This
they
is
won't
all.
rotate.
Yeah, this is all about the maximum probability of finding a molecule, right? At a given time. This is the maximum probability the molecule will be in the solution at a given time. It doesn't mean that the molecules are freezed out like that. Okay? They also move around. Okay. Now we have. Can I go to? So in tri-substituted, what you should be careful? Tri-substituted, you should be careful with your small R groups. Okay, substituent. If it is hydrogen, deuterium, fluorine, please think that it is all looks like an hydrogen, small atom, so rotation will be there. So please don't jump into optical activity and say the given compound is optical active. So mono, bi, no need to worry. Directly you can say the compound is not optical active. But if it comes to tri, please ensure that look into the substituent, and if it is not hydrogen, deuterium, fluorine, then you decide that it is optical active. Okay? Fine.
Sir,
Now you
Sir, found out in the previous page.
yeah.
sir,
Sir,
bi will
in
be
try,
always inactive.
What?
So bi substituted biphenyls will be always inactive.
Yeah, most of it. Yeah.
Suppose, sir, we have sulfonic acid instead of carboxylic, then it
Yeah,
become optically active, right?
yeah, it doesn't become, because that time we will give you a condition at lower temperature that we don't have right now. Okay, that is for your higher level. Huh? So we will give you the temperature at -10. If you have two sulfonic acid, definitely you can separate them, or you cannot separate, but you can see the racemization, a little bit of R and S excess. Okay, but right now you don't need to worry about it. Fine.
sir, in try, can you repeat which is chiral and which is not chiral? I am still confused. Means I understood the rule.
Yeah.
But
So if I look into the first molecule, okay, what happens is first molecule, you think it's a bulky group. This one is bulky, so definitely there will be a steric repulsion, and I consider this to be little bit bulky. So here repulsion will not be that great. It will be a small repulsion, but still there will be a repulsion. Okay, but if you come to this guy, hydrogen and deuterium, there will be no repulsion at all. Okay, they will be happily moving around. They can stay like this forever. Not ever, they can stay like this because there is no repulsion in between these molecules. Okay, they can exist like this. Here also there is no big repulsion between this, because fluorine is a small atom like hydrogen, not like hydrogen, but little bit like hydrogen. So there will be no great repulsion here. So the molecule doesn't need to turn around. But in this case, you see the molecule has to turn around. One has to go to perpendicular to keep the nitro group away from this nitro group. Okay, and even the chlorine has to get away from hydrogen. Even the repulsion is less, but still if it is get away from the hydrogen, it will be happy. So that's why this molecule exists as appropriate isomer, and this exhibits optical activity, whereas this doesn't exhibit optical activity. Clear?
so, sir, out of 4, if 3 are bulky, then it is chiral. Means
Yes.
if they are satisfy the
Yes.
condition.
Yes.
Excuse me, sir. In the fourth example, if in place of fluorine there was a carboxylic acid group, then in that case will it be chiral? Because
What
NO2
happened?
and
That's why I'm
COOH.
saying in tri-substituted, if I have a carboxylic acid here also, so I will consider this deuterium as what? I will consider this deuterium as basically there's no repulsion. Here, yes, as you say that there will be a repulsion, definitely between a carboxylic acid and a nitro group, there will be a repulsion. For sure it will be there. But this can be overcome by room temperature itself. It's enough. Okay, to rotate. Clear?
And sir, C2H
But
also
if
can
you ask
form
me,
hydrogen
sir,
bond
this
with NO2.
molecule at minus 10 degrees Celsius, how it will be? I will definitely say yes, this molecule will be optical active. You can see both the enantiomers of this. Clear? I am talking all of this concept with respect to room temperature. Please, sir. Okay?
Sir,
And you will
in
be
last
asked only
example,
room temperature.
hello sir.
Yes.
Sir, in CO2H and NO2, these can form hydrogen bonding. Rotation will.
Yeah, biphenyl systems doesn't exhibit that much. Um, okay, and nitro groups are not that strong to make a nitrogen bonding. Okay, yeah, it's good thing, but I don't see biphenyl nitrogen bonding is that effectively dominating. Okay.
No, sir. I'm saying it will inhibit some about some rotation.
Yeah, sure. It can.
Sir, excuse me.
Okay. So I will go for the tetra substituted. Okay.
Sir, can you explain how can there be plane of symmetry in biphenyl? That second
What?
case.
What?
In biphenyl case COH, how can there be a plane of symmetry in previous slide?
The plane of symmetry you have to make all in the same plane of the molecule. Okay.
Both won't be in the same plane, no, sir. Both rings.
Which one?
Both rings won't be in the same plane.
Both rings will be in the same plane. That's why if it is in opposite plane, then you will get enantiomer there. Okay. Both rings will be in the same plane. They will not be in orthogonal to each other.
Due to rotation.
Yeah.
Okay.
Okay. Now, if I, for example, for your question, next class I will take the model. Okay. I will show the dicarboxylic acid. Don't worry. I will show the plane of symmetry there. Okay.
Okay.
I will bring a PPT. Don't worry. I will make it. Any doubt, please ask me. Okay. That's why we are taking class. Don't hesitate to ask doubts. If I don't have a correct slide, I will bring it next class. Okay. Don't worry for that. Okay. Now, if you have a tetra substituted system, so I have a carboxylic acid here. I have a tetra and chlorine, nitro, bromine. So we can directly say this molecule is what this molecule is. What is the system? Chiral or chiral?
Chiral system.
Very good. Okay.
Chiral.
Okay.
So am I
Now,
audible?
yeah, you are audible. You are audible.
So I was actually saying chiral, but my mic was not working.
Okay, fine. Okay, it's allowed. No problem. Okay, tell me this is, I make this system very nice system. This was also asked in the exam, okay, in JAM for MSc. So, is this molecule chiral or achiral? Chiral or achiral? What both the reason I am getting?
Achiral.
Fluorine is there.
Because
It is very small.
Achiral.
yeah, this is fluorine. I will consider this as more like an hydrogen. Okay.
Yes.
So the molecule becomes achiral because of the rotation. So it's very clear now. So mono di system, I will be
rotation
saying,
along with that center of
yeah. So I will say that mono and di systems are basically achiral. I will close my eyes. I will go for achiral there at room temperature. And for tri and tetra substituted system, I will look into the substituent. If the substituents are not hydrogen, deuterium or fluorine, I will go for the chirality and say that it is optical active. If it is hydrogen, deuterium and fluorine, I will not say them as an optical active molecule. Clear, sir? Okay.
Yes, sir.
Now, yeah.
Yes,
Now
sir.
to yeah. Now to
Yes.
make us to make you little bit complete. Yeah, that's fine. So, so are we clear?
Yes, sir.
Any doubt?
No, sir.
No, sir. Okay. So
No.
I will draw a molecule. You better tell me what it is, if you are clear. Hmm. This molecule?
Sir, chiral.
Chiral, sir.
Chiral.
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 So it is a, on what basis you said it is chiral? Because you said it is a tri-substituted system. I will consider this as hydrogen, but still it is tri-substituted system, right?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes.
Yeah, be clear with that. Okay. I don't want you to miss any of these questions. Clear? I want you,
Yes, sir.
because biphenyls will be asked definitely. Allenes, biphenyls, you can see two questions. Either they will be, you will be given together and asked to find optical active molecule, or they will give two biphenyl and ask whether it is enantiomeric pair, diastereomeric pair, and all these things. But before in hand, you should know the molecule is chiral or not. Or sorry, optical active or not. Clear? So can I go forward now? So that's
Yes, sir.
why I took lot of time here. Mono, bi, tri, and tetra. Okay?
Yes, sir.
Yes, sir.
Hello, sir.
Yes, sir.
Sir, please show the previous slide.
Yes, previous slide. Yes, sir.
Sir, in this, the encircled one, if we replace tritium with fluorine, then it will be chiral.
Which one chosen? I didn't got you.
So in the circled one,
Which one? The second one. Yeah. Second
yes,
one
sir.
or third one?
The second one.
Yeah.
So if we
Tell.
replace those tritium atoms with fluorine, then it will
Yeah,
be chiral.
yeah, definitely.
But-
No, no, no. What you're asking? You want to replace this fluorine by what?
Sir, it is tritium, na?
No, no, no. This is fluorine.
It is
F,
fluorine.
F. Fluorine, fluorine. F.
So we initially called it achiral or chiral.
Yeah, chiral.
Sir, but I
This is more
I
like a
searched,
hydrogen.
so I just I searched it online, so they are saying that it is dissolvable at room temperature.
This molecule.
Yes, sir.
Don't worry. Okay. This is all we have. Fine. We have all the literatures. You don't worry. That's why we are asking them. Fine.
Okay.
This molecule, don't worry. Okay. This this will be is resolved only if I go around less than, I think it should be going around 20 to 10 degrees Celsius. Otherwise, this will not be able to resolve. Okay. So in RT, it's very tough to resolve them. They racemize. If you resolve also, they will racemize very fast. Hmm? They will racemize very fast. Even if you resolve in room temperature, this will racemize very fast to give you back to your, you will get a racemic component. Fine?
Sir,
This
I
is all
have a doubt.
yeah. Yes.
Won't there be hydrogen bonding to some extent in this case?
Yeah. Don't look into much hydrogen bonding in biphenyl systems. Okay? Hmm?
Okay, sir.
Excuse me, sir.
So whatever I am saying, just follow that, okay? Because this systems which have been, all these things have been discussed nicely, and they have been literaturely known, and people have done room temperature study, lower temperature studies. People say that it is resolvable, but it is not resolvable. Only at lower temperature you can resolve, but in room temperature they will racemize very fast. Okay? Okay, sir?
Thank you.
Yeah.
Yeah.
Yes, sir.
Excuse me, sir. Hello.
Yeah, yeah.
Yeah,
Go
sir.
ahead, go ahead.
This is Salman here.
Yes,
Sir,
Salman.
you
Finally, you
called me.
joined. Thank you, Salman. I didn't
Actually,
remove you,
sir,
Salman.
that time, sir, there was a power cut in my area, so I had
Okay, sir.
to join
Okay, sir.
late. So I'm sorry
Don't
about that.
worry about anything. No, don't worry about the attendance. Everything I will take care. But if you have any doubt, you can ask me at any time. Okay, Salman?
Yes, sir, sure, sure.
Okay.
Thank you very much.
Okay, Salman. Thank you. Okay, now shall we go and find out the head and tail? How to designate R and S of biphenyl?
Yes, sir.
Yes, sir? Sir,
Yes, sir.
what you do, if you have any doubt, find it out. Next class when I come, you can ask me from biphenyl. Sir, ye kya hai, wo kya hai? Sir, if you have this substituent, I'm ready to answer. Okay? If I don't know, I will definitely say I don't know. Then I will go back and collect the information and come to you. Okay? Is it
Yes,
clear,
sir.
sir? Huh? I will go
Yes,
and
sir.
look into the literature. Don't worry. Now, what he said, this fluorine, carboxylic acid, and fluorine, it remains in my mind. I know that it goes to lower temperature, you can separate. But I will go again and confirm, and again I will come back and tell you. Okay?
Yes, sir.
Sir, that's
Sir, I
sulfonic acid also.
Okay. But in your exams, we won't give you that type of molecules. We give you a molecule which is clear cut, not isolable or not. Okay? This is for practice. I am
sir,
giving so
I
that
think
you are
in
clear with that.
fluorine case he is considering hydrogen bonding, so that's why he has shown that it is chiral.
Okay, I will also check that also. Okay? Hello?
Yes, sir.
I will check and also I will tell you. Fine? Okay. Can I go now to RNS?
Yes, sir.
Okay. Now in RNS, same like allene only, don't need to change anything. The only part when we give RNS, we ensure that we give you this one, okay? One will be the wedge one, another will be the dashed one. Like that only most of the time it will be given. Fine. So if I give you nitro carboxylic acid, nitro bromine or okay. Fine. Now what is our rule for allene says? First, what are the rule? Can you
Wedge and dash.
refresh?
Wedge and dash.
First you have to see the molecule from tail to head. So the tail will be the substituents where it is on the plane. Head will be where the substituents are projected in the dashed and wedge. That will be the first thing. So that is our first rule. We have given that. The second rule, what it says? The numbering will start only from the tail. Right?
Yes, sir.
Yes. So this will be 1. This will be 2. This will be 3. And this will be 4. Am I right with the numbering?
Yes, sir.
Yes, sir.
So now I will leave the 4. So I will rotate 1, 2, 3. So if I rotate this 1, 2, 3, it will be like this. So it is clockwise or anti-clockwise? Anti-clockwise. So it should be yes. And then the third rule says what? The lowest priority group should be the dash form. Here the lowest priority group is in the wedge. So then I have to change the stereochemistry to R. So that's all. For it follows the same rule, nothing different like allene. Okay, same like biphenyl. So now can we do some problems?
Excuse me, sir.
Yes.
Sir, how is the second benzene ring? One bond is about the plane, one is towards the plane.
Not that bond.
How to visualize that?
Yeah, normally we put this one. Basically, this says this substituent is above and this substituent is below. That's what we say.
Sir,
Okay?
we can visualize it by saying one is away from us, one is towards us.
Yes. That also you can say. No problem. Anything? Doubt? Now you guys are.
Sir,
this represent. Yeah.
So this representation will be always given, like in the first slide that
without this representation, I cannot ask the question at all. Okay?
Sir, actually, the first slide that you showed, where this biphenyls is introduced, there was another kind of representation, like one side of one benzene was wedged and another side of another benzene was wedged. So that kind of representation, what to do with this?
No. That won't be like that. Okay? Because we know how you can visualize. Okay, you guys. So, for example, if maximum happens, I can give a molecule like this. I will give you the. We might see the. I'm telling the possibilities. Okay, by which we can give you. So sorry, this will be dashed, and this will be wedged, and this will be dashed, and then you will have a biphenyl like this. So other way around, we can give you just to check. Bromine, chlorine, bromine. Like this we can give you just to check. Then you will be seeing from this direction, right? Yes?
Yes, sir.
This will give
another
sir. Way how we can give you. Just a minute. I will show you the possibilities by which we can give you the molecule, because my friend asked this question, so I want to sometime to check you out, not more. Sometime we might give you like this also. Okay, there's some way of doing it, but still we don't, in IITs we don't prefer this. I have seen, but in some universities people are giving like this system. Okay, sometime also it will be given like this, or sometime you make it vertical, this whole system as a vertical and give. This is the only possibility way we will give you. Okay, any ideas?
Okay, sir.
So in the second part, how that means that the phenyl is in this plane, but the bromine and chlorine are getting away and towards it. And how is it possible?
So again, you don't think about anything. Just look. This will be your tail, and this will be your head, right?
Okay, sir.
Okay. So then you go with the same numbering. So the numbering will be 1, 2, and here it will be 3, and it will be 4. So you will have 1, 2, 3. So this will be anti-clockwise. So yes. Now the lowest priority group is in the dash, so it remains as A system. Okay.
Sir, in second example, I think there should be one bond in wedge of phenyl, because then it will be easy to visualize that one plane is perpendicular to another plane.
One bond is?
Sir, in second example,
it is wedge only. I have written proper. I have not written this properly. Okay.
Second example, right side.
This one, this we won't give it, man. Don't worry, we don't give it this way. You cannot give it actually, but this is somewhere it is giving. I don't accept this form, and we never give this. Okay, don't worry.
Excuse
this is
me,
the
sir.
I don't believe this way. Okay, this way you cannot visualize at all. Okay.
So that representation also is wrong as well, because the phenyl ring is on wedge dash, not the substituents.
Yeah, that's why I'm saying.
Yes, so that is only I was.
I have seen in some question papers. That's why I'm saying this is where some people are giving. I don't believe that. So the only two ways we give is that we like to prefer this way. This is the right way you can give. Another is this. Okay, that's all. Or you can make it vertical. That's all more. Don't think about this. Okay. Yeah.
Sir, the first example, it won't have center of symmetry the way you have shown.
I'll see. That's why I'm saying if you have 4 substituents, don't think all these things. Okay.
No, sir. In now recent example, that BrCl and ClBr.
Yeah, this
may have center of symmetry.
Center of symmetry. I was not talking any center of symmetry here.
So we may join BrCl.
Distance of bromine from a plane and it is above the plane, so distance will not be same, I think.
I think he is considering this to be the same, no?
Sir, is it chiral?
Yeah, it's chiral.
So it will not have center of symmetry, right, sir?
Yeah. But
It should have, sir.
always take the plane of symmetry, which is very important. Okay. Plane of symmetry, if it's there, you should be careful. Otherwise, don't need to be careful. Try tetra substituted by biphenyls. Most of the time, you have an atrop isomerism. Okay. So it's very rare to see an optical inactive molecule in tetra substituted. Very rare to see. Okay. Okay, guys. Are you guys are
yes,
okay?
Sir. Yes, sir.
Okay. Okay. Now, if I draw molecules, can you help me out to find it out whether it is chiral? All these things. Okay. I'm going to write molecules so that you are going to tell me very fast what are they. If you help me out, then what about this?
Chiral. Chiral.
Sir,
Can I write AC? Huh?
Chiral.
Okay.
Yes, sir.
See, this is the molecule what my friend is asked. One of my friend asked that. Yes, I got that molecule. I have written this molecule. I think, sorry. I will take another slide. One of my friend asked this question. I have the same one, so that I can, by saying this itself, I can clarify his doubt. I have taken this piece of example. Just you have to answer me. I will finish off the question. It was in UPSC. It was in UPSC. This question was UPSC civil service. Okay, IASI. I think that's why it came for this. Same question was there in UPSC. But the question was different, my friend. The question was said that comment, is this resolvable at room temperature?
No, sir.
No, sir. No, sir.
It's not resolvable. Okay. At room temperature. What is this?
Sir, it is resolvable.
Sir, not resolvable here also.
Not resolvable.
But, yeah, I will tell you the answer, how to write
Not
this answer. Resolvable at room temperature. You see, this is what it is written in the textbook, at room temperature, but racemize very fast. Okay, so that's what I told you. One of the student asked this question. Are you getting that? Hello?
Yes, sir. Yes, sir.
Yes. Yeah, resolvable at room temperature, but racemize very fast. This was the answer given for that. Okay, but they said the molecule is achiral. Finally.
Yes, sir.
Okay. What is this? It is resolved at
chiral.
So when they asked for chirality, they said this is a achiral, and this was chiral. So the question was like that. So they were asking resolvable nature of this three, and they were asking chirality of this three. Okay, and the answer was like this. That's why I took this question. Very good. Now I think I have clarified your doubt, right?
Sir, there won't be plane of symmetry in third case.
No, right. That's why tetra substituted systems, you should be really careful in tetra substituted systems. You don't see this this plane of symmetry, all these things, because the molecule is completely orthogonal. So you guys are seeing that it is both are in the same plane. Once it gets away from the plane and becomes orthogonal, it's very tough to get plane of symmetry, center of symmetry. Okay?
Yes, sir.
Tetra substituted system, you can go blindly and say it is optical active. See, tri and tetra substituted, only one thing you have to remember is that you have to remember that the substituents are smaller or bigger. Okay, if the substituents are smaller, then you put your mind. Okay, if the substituents all are bigger, then you can close your eyes and go for chirality. Don't think of plane of symmetry. Okay, it rules out because of the orthogonality of the ring. Don't confuse yourself too much. Okay, don't get confused because we have seen all these systems a lot. That's why we are confident. When you are going for tri and tetra, just look into the substituent size. If it is not hydrogen, deuterium, tritium, fluorine, close your eyes and go for the chirality. Okay?
Excuse me,
it
sir.
Sounds correctly.
Yes, sir. But apart from that bulky group, we also have to look for A not equal to B and C not equal to D.
Yeah, that should be definite. That is the first rule. That you, without that, you should not go away, because that I started with the mono substituted itself. Okay? That is number one. That is rule number one. A should not be equal to B and C should not be equal to D. Then comes the second, third rule. Okay? Don't confuse too much with the symmetry. It doesn't work that great.
Yes, sir.
Okay. Okay, sir. So we are done with the two systems, that is allenes and biphenyls completely. Okay? So what I will do, I will ask the research scholars to take you to allenes and biphenyls problems and you try to answer there. If you are not convinced, you can come back to next class and we can discuss. Okay?
Sir, one thing, can you ask the TAs to share the slides, because those have some questions.
Only once I finish my PPT of stereochemistry, then only they will share the slides. So I will definitely tell them to share the slides tomorrow. Okay?
Okay, sir.
No, sir, tutorial slide.
Yeah, tutorial slides. Tomorrow class they will share it. Okay?
Sir, will you upload this one also in the?
Yeah, this one I will upload today itself. Once my class is over, I will upload. Okay. So, are you happy with what we have studied so far about isomers, optical isomers?
Yes.
So we are done with chirality, we are done with ionostereomers, we are done with diastereomers. We have seen chirality of molecules with non-stereogenic centers. Okay. Now, the one more thing which I have to introduce is geometric isomers. I think we don't need to spend much time on this. You guys know this pretty well. Okay. Geometric isomers are, what are geometric isomers?
Sir, isomers that have different atoms like separated in space and that.
Yeah, can be,
I don't know the exact definition, but
yeah,
spatial arrangement is different.
Yeah, all are right. How you designate them?
Zusam and Antigigan.
Very good. So it should be, initially it started as cis and trans, but later on that nomenclature of cis and trans was not that effective. So people are started using E and Z. Okay. So the same thing works here. So you have it should be basically for a double bond system. Okay. Don't, the first rule is that the X and Y should be a double bond system. And then you take a single atom and you go with the CIP rule as we go for allenes and biphenyls and put 1, 2, 1, 2. And but in this case, you see whether this 1, 1 are on the same side, then you call them as Z. That is, Z means it is all together. And if the E and 1 and 2 are opposite, then you call them as E. Okay. So this is E and Z. For example, you take a Z together and E is opposite. Okay. I think you have learned this more, right? Okay, tell me what is this? How you can number this? So here the CH3 gets the number 1,
Yes,
and
sir.
this will be 2, and this will be 1, and this will be 2. So both the 1 are both on the same side. Then I can call them as
Z.
G.
Z. And this one? So hydrogen will be, in this case bromine will be 1, hydrogen will be 2, in this case chlorine will be 1 and fluorine will be 2, right? So
E, sir.
very good, that's all. Okay, so I think either there is nothing need to explain. You tell me what it is immediately. Should not think too much.
Z.
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 Yeah. This one?
Z again.
Sir, Z.
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 Sir, it will be E.
3.
E.
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 This one?
E, sir.
This one you should be
E.
very careful.
Sir,
It will give you
E.
like that.
So there will be
Here you
2.
have 2 double bonds.
Sir, both will be E.
Both are E,
That,
sir.
that will be very important. Okay. This type of question you might end up in getting, where you have 2 double bonds. What you do, pata hai? You will write only for 1 double bond. You will not write for another double bond, and you unnecessarily lose half mark. Okay, so there might be 3 double bonds, and there might be. We will give you a molecule and we will ask designate E and Z of all the given structure. We will say. So you have to designate for all the double bonds and triple bonds wherever it is there. Okay, sorry, double bonds. Yeah, triple bond also you can designate there. Okay, all double bonds you have to designate. Okay, fine.
Yes, sir.
Fine. So that's all geometric isomer. I think geometric isomer is not much thing, but just I want to introduce the E and Z term so that you are clear. Okay. This is just sometime you might end up in getting in objective questions.
Sir.
Can we resolve inertiomers? Because that time one of my friend in the first class, he asked me, sir, inertiomers are having same physical and chemical property. How you are saying that it can be separated out? Then I told him, yes, there are many techniques by which we can separate. Okay. The technique normally what we use to separate inertiomers is that we will take the inertiomers, okay, and we will try to react it with a sort of a chiral compound. And for example, you take here we have a 2 inertiomers, right? One is S-butanol and another is R-butanol. Then we take a inertiomer of tartaric acid, which is RR. Then we react with this compound, with this mixture. So we will get here what we will get, SRR and RRR. So these two are now diastereomers. We know that diastereomers can be separated out. So we will separate these diastereomers and then we will hydrolyze, because we know that the ester can be hydrolyzed very easily. We can hydrolyze this ester and then we end up in separating S-butanol and R-butanol. So basically what we do, we will take SR, treat it with a tartaric acid RR ka, we make them as a diastereomer. Then we know diastereomers can be separated by selective recrystallization. And then we hydrolyze them, get back our alcohol. That's the way we separate. Because this is the first question. Once I started, one of the students asked me. So that's why I also have this slide just to explain him what to do. Because I remember that question because I wanted to answer that. So inertiomers, I have to convert it to diastereomers and then separate it out and then you bring back to the inertiomers. Is it clear, sir? This part?
Yes, sir.
Okay. Yeah. Now someone was asking me something he was saying. Anything?
Sir, I was saying that this geometric isomers can be present in like odd number arranged systems also, right?
Yeah, geometric isomerism. No problem. Odd number you call as cumulines. Okay, then you have to. He asked a very nice question, which has to be answered. I think many people understood what he asked. Any of you understood what he asked?
Yes.
Sir, yes, sir.
Yeah.
Yes,
Yeah.
odd number of double match.
Yes, yes. Because he asked
The
a very nice
cumulus.
question. Cumulines, yeah. What is that? Because some might not know it. For them, I am writing. So, for example, we have these Alin systems, right? We have these Alin systems, and we said that these Alins are there, hydrogen and chlorine. We can have Cl and Br, whatever it is. Okay, we say that we can have an alene system like this, and then we go for Rs, right? But if we said that it should be even number, then only we will consider as an alene. His question was that, sir. So how? So this is called cumulines. Okay. Here, instead of doing like alene, we can use the E and Z formula. That's what he asked. If it is an odd number, here the double bond is odd, right? If the number is odd, then you go for EZ configuration. If it is even, then you are going for the alene type of thing. Odd means you will go for E and Z. That's what he asked. It's a very good thing. Very nice thing to ask. So it will be 1, 2, 1, 2, and then you know that it is Z. Right, sir? So this type of questions you should ask me, so I will forget in between. Huh?
The same will be in the ring case also. That is odd number ring will
yeah, you can extend that things. Yes. So what is the time now?
11:18.
11?
18.
118. Okay, fine. Still I have some time. So that means I am coming to the end of stereochemistry, sir. So we are done with stereochemistry. If you have any doubt with respect to stereochemistry, please don't hesitate to ask me. I will be happy to answer at any time. Okay. If you want me to take some class extras, I'm ready to take, but I think we have a lot of classes already taken. So I don't think you need any extra class, but if you need also, I am ready to take, because my idea is to make you to be comfortable what you are studying with. Clear? Clear, sir?
Yes, sir.
Okay.
Yes,
Can
sir.
you see this slide? This particular conformational slide? No, no?
Yes, sir.
Yes, it's very good. Okay. So then we start.
We can see the EZ slide.
Oh, achha, then I have not shared it.
Yes, sir.
Okay.
Sir, in resolution, can you just explain the recrystallization part once again?
Which part?
Like there was a last paragraph.
Yeah, recrystallization is basically what happens. It depends upon the solubility. If a compound should be, see, for example, if the compound should be minimally soluble, and one, if it is maximum solubilized. If it is solubilized minimally, it sort of bumps out. For example, you take a compound and the compound is completely soluble in a given solvent, then doing a recrystallization will be tough. But if you take a compound which is partially soluble and you warm it and then it becomes completely soluble, and then you keep it in the fridge or in room temperature, then the compound comes out in a slow crystalline fashion. That's called as recrystallization. Okay?
Okay.
So now for two different diastereomers, the solubility definitely varies. One will be highly soluble in the given solvent, and another diastereomer will not be solubilized in the given solvent, the same solvent. Okay, so you take a methanol. One of the diastereomer will be completely soluble in that methanol. Another diastereomer will not be soluble. It will be partially soluble only. You warm the solution, then both will be soluble. But after one day, the one which was partially soluble will be coming out from the solvent, forming like a crystal. Then we take the crystal out. Okay.
Okay.
Fine.
Okay.
Okay.
Yes, sir.
Yes, sir.
Yeah. Then slides. I hope now you can see the slide, right?
Yes, sir.
Conformation
Yes,
analysis.
sir.
Okay, this is the second part which I am going to take. So we are done with the sort of isomerism, which is static stereochemistry. Most of the time it is static stereochemistry what we have dealt with. Now we are coming for this conformation analysis. This is also very interesting thing to study. Okay, um, so you guys know the conformations of alkanes and cycloalkanes. This is very important, and most of the time this particular conformation misleads us in many of our reactions. Okay, this is mainly because what are conformers or rotamers? We call them as a conformation, or you can call them as a conformers, or you can call them as a rotamers. Like you call them enantiomers, diastereomers. Here we call them as a conformers or rotamers. Basically, what it is that the different spatial arrangement of a molecule that are generated by rotation about single bond. You see this word, rotation about single bond. That means most of the time your alkanes, cycloalkanes, that means they keep on rotating, right? Because there are single bonds available there. They end up in sort of rotating, and you end up in different rotamers. And then the problem comes really with the reactions, separations, and it will be a very hard technique to understand also. So normally that's why I said a molecule is not a freezed out a system. It's not like a freezed sitting like that. No, it is not freeze. The molecules does a rotation, it does vibration, it does many means of thing when it is in a solution. So rotation about a single bond is very important phenomena, and it should be understood very importantly, because you should know the reactivity later on. Okay, I will teach you the reactivity also, all these things. Take this is a simple ethane molecule, right? Fine. Now in this ethane molecule, what happens? This ethane molecule, this CC bond, okay, rotates to end up in giving you with lot of conformers or rotamers. Okay, this is very interesting. Okay, I will see there are many ways you can project this formula, this rotamers. People say this is an eclipse form because you can see that all the hydrogens are being shaded by the front carbon or hydrogen, like sun is coming before a moon. Okay, this is the best way of seeing the eclipse form. Okay, you see all the hydrogens have been eclipsed. The front carbon hydrogens have been eclipsed by the rear carbon hydrogens. That's why we say that eclipse. Eclipse is basically, you know, that sun coming before moon or moon coming before sun, whatever it is, that type of eclipse one. Okay, this is not interesting, but still you know the meaning of it. It is eclipsed. There is staggered, where all hydrogens are away from each other by at least 60°. Then you call them as a staggered form. Okay, fine. This is also well and good. If you rotate, you end up in getting it. So ethane basically have two rotamers. One is eclipsed and staggered. Okay, fine. That is good. This is one way of projecting it by stick model. You can project by Newman. This is the best way you can project a molecule. I like this way. You can adapt any technique you want, but I like this technique because Newman projection looks very nice. So Newman, I can project eclipse like this and staggered like this for ethane, which you have studied. You can also do by Sawhorse. Some people are I think the old chemist, okay, earlier 1980s Mapura, people like to write in the Sawhorse method because I think they like this way. But I like to keep it in Newman. Okay, people use Sawhorse also. Okay, fine. This is all well and good. This is all the projections. But the real now things comes. Okay. Don't go with the slide this term. Okay, I will come exactly now. Tell me the stagger and eclipse form. which form will be stable?
Staggered.
Staggered form is stable. Very nice. Staggered form is stable compared to eclipsed form. Very good, very good. Now, this is a straight explanation, right? Why?
So eclipse form there is no
Due to repulsion.
Sir, in eclipse form there is no electronic repulsion. That's why it is not stable.
In eclipse form, what is there?
Sir, repulsion.
Repulsion. Repulsion. Okay. Repulsion of what?
So basically, like there was an explanation in Solomon's where they said that the bonding electrons in eclipse form can interact with the other bonding electrons and they repel each other.
Okay.
So that is why it is not stable.
Okay. Sir, you guys are understanding what he said. He said that the bonding electrons, you have to understand, I'm not talking with respect to the I'm talking with respect to the electrons, okay? The bonding electron of one substituent has a repulsion with the bonding electron of nearby substituent, okay? And how far this repulsion will be there, this is very important, and this is called as an ecliptic repulsive thing. It's called as eclipse repulsive factor. What do you call them? Eclipse interaction. Normally, I don't use this word of repulsion, which I never liked that. Okay, I always use this word of eclipsing interaction. What I use? Sir?
Eclipse interaction.
Yeah, it is an interaction rather than calling them as a repulsive. It's because if you go for higher studies, then you know that these factors will help in stabilizing rather than destabilizing. Okay, that's why it's better to call them as an eclipsing interaction. And this eclipsing interaction, or we call them as a torsional strain, and this happens within three covalent bonds. The two atoms, the electronic clouds of these two atoms should be only within three covalent bonds. Then this repulsion happens, that we call as a eclipsing hydrogen-hydrogen eclipse. In this case, it is hydrogen-hydrogen, so you can call them as an hydrogen-hydrogen eclipsing interaction. Okay. Now this is nice for your explanation for your eclipsing. Now you tell me why staggered form is stable.
Because staggered form are away from each other.
I didn't got that answer. Hello? Some noise?
Sir, am I audible?
You're audible, but with some internal noise or something. Okay, fine. Any other guys?
Sir,
In one
staggered.
I had in one book I found this explanation that in staggered form the antibonding MO actually interacts with the bonding MO because they are in opposite directions, so they
fine.
face each other.
Very good, very good.
This interaction stabilizes.
Very good. So what? See, many people when you write, see why I am focusing on this too much. You should think why this sir is focusing. What is this big thing? It's a torsional strain, okay, or it is an eclipsing interaction between two hydrogen atoms with three bonds. What is new here? Okay, you can ask me now. If I ask, we ask questions on this type only, but I don't get any answers. When I ask what is the stabilizing factor for staggered form, you guys write an answer which is typically wrong. You guys write that there is no repulsive force, there is no torsional angle. Come on, man. That is the answer you write. We ask in filling the blanks, or we ask like that. Then you write there is no eclipsing factor. Come on, man. Eclipsing factor is destabilizing this. I can understand pretty well. But which is stabilizing the staggered form? That is what I want to know. Nah? And you are writing that it is absent. That I know it is absent. But what is stabilizing here? The stabilizing fact is that when you have a bonding orbital, definitely you will have an anti-bonding orbital, and that is what we wanted you to think. If you have a sigma, you have a sigma star, right? Which is an unfilled orbital. Now you see, now what will happen? This sigma bonded electron will now get stabilized. That's why I said I don't use this word torsional strain. I use the word eclipsing interaction, staggered interaction. That's why I told you. Now you understand why I use the word interaction rather than these words. Because here it is a repulsive, but still it is an interaction. Here it is also an interaction. Okay. Here what happens? A filled orbital is interacting with an unfilled excited orbital, that is sigma star, giving the stabilization for the staggered form. See, I have told you again we will ask you in the filling the blanks. Again, you write that there is no eclipsing factor, there is no torsional strain. Please don't do that. The staggered form is getting stabilized only because of the interaction between the sigma and sigma star. That is the filled orbital and the unfilled orbital. This is what we wanted. The stabilizing interaction between the filled CH sigma bond and empty CH sigma star antibonding orbital. Anything? Any doubts, sir?
No, sir.
So you will write the right answer, na?
Yes, sir.
Okay.
Yes, sir. I had one question there.
Yes, sir. Yes, sir.
I had this question in class 12 only. Here we know that the bond order would depend, like the stability would depend on the number of electrons in bonding minus antibonding divided by 2, right?
Yeah.
So if the number of electrons in bonding decreases and antibonding increases, the overall stability of the molecule would decrease.
Yes.
But here, if the bonding, like filled bonding orbital and the unfilled antibonding orbital interact, so the electron is basically transferred from the filled bonding to the unfilled
antibonding. It's not transferred. So please try to understand there is no transferring happening here. Okay. This is only a two electronic clouds coming together and merging each other. Okay. One electron cloud having a strong density, another electron cloud which doesn't have any density. Now they merge each other and get stabilized. Okay. Still the electron density is with the hydrogen. The more the electron density on the hydrogen gets scattered around. Okay.
Achha.
That will be the best answer. Fine.
Yes, sir.
Okay. Now, what else question I can ask from here? Right? So one question in the evening I can ask this. Huh?
Sir.
What?
Sir, what interaction between sigma and sigma star is happening here?
You have an electron dense cloud, right? And you have a cloud which is not dense at all. So this electronic cloud which is dense will be scattered around to the electron less dense cloud. So this interaction we can call them, it's an interaction. Okay. We call them stabilizing interaction, but still I call them as an interaction. That's all. Fine. Because sigma star is empty, right?
Yes, sir.
Yes, sir.
So
what
will it
other
share
question
the
I can ask from here?
Sir, will it share the electron to antibonding orbital?
It will not share. That's what I said. It will not share. The electron density will be dispersed. Okay? Electron is not one, as you see. Electron is like a cloud. It will be more dispersed. Okay?
Okay, sir. Okay.
That will be better. Any other question I can ask from here? Any question? You tell me what question I can formulate from here. No one? No one wants to formulate a question? One question is that I will ask why staggered form is stable. So you will be writing this answer. Any other question?
So you can ask for any special case, not like ethane.
No, ethane if I want to ask. What can I ask?
Sir, we can
comment about the bond strength of CH in both the cases?
Bond strength is related to this one, bond strength.
Yes, sir. Sir, because
So we can ask.
Strength of the bond doesn't relate to the rotamers, right? Rotamers, conformers.
So we can ask like when the energy of the molecule will be the greatest in which conformer.
Okay, very good. You can ask that question. I can ask you what will be the energy difference between the staggered and eclipsed form, right?
Yes, sir.
So what is the energy difference?
So
The stabilization.
Kitta energy number? I can ask the number, right?
Don't remember,
Roundabout
sir.
number. Huh?
Sir, I don't remember the energy number.
Yeah, that's good. You guys don't remember. That's why we asked the question. Okay. So what I want to teach you here, I want you to remember this energy numbers, and you remember this with. So this will be useful for all the propane, ethane, butane, pentane, everything. Okay. So please remember this. What I am writing right now. Okay. See the hydrogen eclipsing. I write all these things. Okay. Eclipsing. I write this word. I don't know, many people don't like it, but still I like this word a lot. Eclipsing interaction. So this will be 1 kilocalorie per mole, approximate energy. Okay. So most of the time people ask you approximate 1 kilocalorie. So when you have an interaction, that ethane, you have seen this interaction, nah? When you have an interaction of this hydrogen electronic cloud and this hydrogen electronic cloud in the ethane, this interaction I'm talking about, this interaction gives you 1 kilocalorie per mole. And this interaction, people call them as a torsional strain or whatever you want to. You can call, okay?
So this is part HH. Like for ethane, there will be 3 then, 3 kilocalories.
Yeah. I will come. I will finish it out so that we can use it for everything. Okay? This is hydrogen to hydrogen. For example, if you have a methyl to hydrogen, then you have an eclipsing interaction. How much you will be thinking? How much it will be there?
So 2.
2. Methyl to hydrogen. Sorry, sir. It is 1.4 kilocalories per mole. Okay? Okay, fine. Because you have a bigger, bulkier group. So electron density will be huge for this compared to hydrogen. So they have interaction.
The dates will be given, right?
No. This won't be given. This won't be given at all. No chance. So hydrogen interaction will be 1 kilocalories per mole. Methyl hydrogen, you can always think that 1.5, but to be honest, it is 1.4. Okay. Now this is very important. Okay, eclipsing interaction, and this also I can say it is a torsional sort of strain because of that. This is a torsional interaction. Fine. Now you come to methyl. If there is a methyl, and then there is a methyl. And these are all 3 bonds interaction. Okay, 3 bond interaction. I am writing here methyl to methyl. That doesn't mean that it is a 3 bond interaction. So this is also an eclipsing interaction.
Sir, what is the 3 bond means?
Huh?
So 3 bond means both the carbons are sp3 hybridized or 3 hydrogen.
Yes. See, the methyl should be like this. 1, 2, 3. Okay. This interaction only I am talking about. Clear?
No.
Sir, will this be 1.8?
I could not understand. Means both are in means both carbons have 3 groups attached to them, right? That is what you mean to say.
Oh, you leave this hydrogen. I'm talking this 3 bonds. Okay.
Okay. Understood. Yes.
Okay. No problem. Now,
so will this be 1.8?
1.8.
So will this be 1.8?
Yeah, this is very
yes, sir,
interesting.
1.8.
1.8. No, sir. Now, this is very interesting. People will ask you this question also. It is 3 kilocalories per mole. See, 1.4, suddenly it becomes 3. can you tell me why this is because of torsional strain, that is we call as eclipsing interaction. This is also only because of torsional strain. That's why we call this eclipsing interaction. But here what is happening? Why it is becoming 3 suddenly?
Sir,
It should be
Van der Waals
1.8 or 2, right?
There was repulsion.
Steric
Van der Waals
hindrance.
Very good.
Yes,
Van der
Van der Waals.
Waals. Yes. Now this eclipsing interaction is constituting by two phenomena here. Torsional strain plus Van der Waals. Very nice. You have Van der Waals interaction. Because the molecule becomes, the size become big. So the radii of 3 Armstrong goes away. Now this can go and interact with this. Because you know that Van der Waals radii is only 3 Armstrong. Up to 3 Armstrong. So if it is crosses 2.5 Armstrong, then they will interact with each other. So now you end up in getting torsional strain plus Van der Waals strain, which is put together as an eclipsing interaction, and this number comes to 3 kilocalories per mole. Okay?
So does that mean that torsional strain itself just contributes to 1.8?
Yeah, something around. Yes, yes. Something around. Okay? Any doubt? Because these numbers is very effective. Okay. Now another interaction I will just tell you, because I know that you guys know about this interaction, but still I want to tell you. This you can see in which system you can see this? If there is a 2-methyl, okay, which is 60 degree or 300 degree, whatever it is, if you do and you end up in getting this 300, whatever direction it is, okay, 60 or 300. If you rotate clockwise or anti-clockwise, 60 or 300. What interaction is this interaction? Anyone can tell?
It's called Gauss, I think.
Huh?
Gauss type interaction.
Very good. Gauss butane interaction, right? Yes or no?
Yes,
Sir,
This is Gauss butane when there is 2 methyls with 60 degree apart or 300 that 360 when you come close to 300, then you end up in Gauss butane interaction, and this energy is how much?
Sir,
Come
4.
on, man. Huh?
Random place. 4.
Hey, come on, man. This is away 60 degree.
2.5.
less.
I thought like, see, methyl and methyl are directly each other. That itself is 3. Hydrogen and hydrogen is directly with each other, eclipsing. That itself is 1. This is 60 degree away from each other. So definitely it should be less than 1.
2.6.
No, man, it should be less than
2.8.
0.9 kilocalories per mole. Because I thought you will understand this. See, in this case, what happens? Hydrogen and hydrogen eclipsing, right? Sorry, this should be not 3 moles. Eclipsing. That itself is giving only 1 kilocalorie for me. This is not even eclipsing. This is away from each other. Still it has an interaction, and that interaction is called as Gauss butane interaction, and that is 0.9 kilocalories per mole. Okay? This energy definitely you should understand. You should know these values.
Sir, but
Yes.
is this for pair of CH3 or is this for like the entire like 3 CH3 interacting with each other?
No, only 2 CH3, not 3 CH. Sorry, I don't. I just for 300 degree I told. It is only 2 CH. Okay.
Sir, are these values in the slide or should we take note of?
Oh yeah, you should take note of all these values. It's very important.
So if it was like 2
And you
CH3
should
like
know
that,
what are their interactions. Yeah.
so if it was 2 CH3, then it would be twice of this.
Yes.
Like
yes,
previous.
Yes, you are right. You are right.
So, sir, these data are not in the slide.
This data will not be in the slide. These are all I am accumulating and giving to you because your class is too good.
Sir, torsional strain is repulsive interaction, right?
Yes.
While Van der Waals is
Van der Waals
attractive.
is also repulsive when the atom comes into the another atom radii.
Okay, both are repulsive.
Yeah, yes, sir. Both are reference. So hydrogen-hydrogen eclipsing interaction will be 1 kilocalories per mole. Methyl-hydrogen eclipsing interaction will be 1.4. Methyl-methyl will be 3. And Gauch-butane will be 0.9. I think it's easy to remember. 1, 1.5, 3, 1. Only you should know that it is less than 1. So 0.9. Okay?
Yes, sir.
Okay, fine. Now you tell me what will be the difference of stagger and eclipse of ethane. ethane का stagger and eclipse का difference कितना रहेगा? Come on, man. What is the difference of ethane? This one.
0.3, sir.
0.
The 3 kilocalorie per mole.
Very good. So how
Yes,
many
sir.
eclipsing
So
hydrogens
three.
are there? 1,
Sir, 3 pairs.
2,
Okay.
3. Very good. So 3 pairs means how much it should be? 3 kilocalories per mole. Okay. So see, it's very important. That's why I don't want
Excuse
you to.
me, sir.
Yeah.
Sir, but how much for staggered? 0?
Stagger I have not asked. I have asked for eclipse now, right now.
Yes, sir.
You
Okay,
asked
sir.
energy difference, right?
I cannot hear you. Noise.
Sir, you asked the energy difference of the staggered and eclipsed, or energy
Okay,
of
staggered.
eclipse.
Staggered. If you consider 0, what will happen? Eclipse.
Then the difference will be 3.
Okay, fine. So can we go and see the values, real values?
Yes, sir.
This is the real value people get. What they got? 2.9. Okay, so we are more or less there, right?
Yes, sir.
That is very important. That's why I said, see, we won't ask like exactly the numbers. You can, but still 3 kilocalories is around the number you are there. So you will be asked questions like this. Okay? Clear?
Excuse me, sir.
Yes, sir.
Yes, sir.
Sir, but for here we also need to know the energy of staggered, no?
Yeah. Most of the time, the energy of staggered, which is the minimum energy conformer, most of the time we keep it as a 0 degree. So it's 0 energy, because that will be the stable conformer we consider. Most of the time, when you consider a stable conformer, you make them as a 0 energy and you talk with respect to that. In reality, that's the way you can do experimental. Okay?
Okay, sir. Yes, sir. Yes, sir.
You need a reference point that will be considered.
So these are those just approximation values that we have calculated, but the observed value is just around that value.
2.9. Yeah. So in exam we will ask, don't worry, in exam we know that you have to calculate with the approximate, how you do experimental, right? It's tough. So it will be 2.9, 2.5, 3.5. Huh?
Sir, at torsion angle 60 degree and 180 degree, energy of molecule is same. How it can be possible? Sir, 180 degree is the staggered form, and 60 degree will be gauged from the.
I'm not hearing you. I think you should check your microphone or your laptop, because I get the sound.
Sir, I am saying that at torsion angle 60 degree and at torsion angle 180 degree, you represented energy of molecule is same. So how it can be possible? 180 degree torsion.
In case of hydrogens, okay, but in butane or propane, if I move forward, it will not be the same. Okay.
Excuse me, sir.
Yeah.
Sir, this energy, total energy of the molecule is calculated experimentally, but in exam we have to take direct sum, or what we have to do, because it's for one interaction.
How I teased you, the same way. Okay. The way I teased you, you do that. See, I am not going to exactly ask So there will be values like 2.9, 2.5, 2 and 3.8. Now you have to figure it out. Okay. Now if you do theoretically, you know that you are coming eating 3, right?
Yes, sir.
Yeah, that's all. This is the best way to go and find out the nearby areas. Huh? So we don't ask 2.92, 2.82, 2.72. We won't ask. Don't worry. We know that. Huh?
Sir.
Sir, so we have
Yes.
to consider one HH interaction independent of other HH interaction.
Yes, 3 HH interaction you have to consider.
Sir, we assume
Okay, sir.
staggered to be means reference, right?
Yes, most of the time.
So
minimum
the
and
values which you give the interaction, so that is also with respect to staggered, or that is absolute?
that is for eclipse one, the value I gave.
Yes, means that is eclipsing interaction for calculation, and here we are
Yeah, that
calculating
is actually
observed
I have
value.
given you a round number. For calculation, I have given you a round number, right?
Okay, sir.
Okay, then. So, yeah, I'm trying to make it simple. Okay, that's why I'm trying to get you these numbers. Fine. Otherwise, you have to keep on memorizing 2.9 kilocalories. When it goes to butane, pura, you cannot sit and memorize all these numbers. Okay. If you use this table, it will be easy. But I won't give this table in exam. You should know that the values. Okay. So for next class, we'll start from butane. Okay.
Yes, sir.
So any doubt? I think this class you might not have doubt, because just remember these values. In next class, we have to use these values and this strain pura. Okay. Clear?
Sir,
Yes.
sir, while calculating the difference between eclipsed and staggered, shouldn't we consider that sigma sigma star interaction also?
That is what we are considering, no? Which sigma
Uh,
sigma star interactions you are talking about?
Sir, that is stable. That why is that staggered stable?
Yes,
That
it is an interaction. That's why I am saying experimentally your minimum energy conformer it is. Okay, so that will be taken as your reference.
sir, but that eclipsed one, that values were absolute, not related to that staggered.
What eclipse one is? No, I'm not getting you.
So the values which you gave, that was for that bond. Were that with respect to that staggered one?
No, no, no. Come on, man. I'm given the bond. I have written very clearly here. It is eclipsing. Written hydrogen hydrogen eclipsing interaction. Methyl hydrogen eclipsing interaction. Methyl methyl eclipsing interaction. I have not talked anything about the staggered here. These are all when they are eclipsing. Then only you can use this value. Okay?
Okay, sir.
This is all eclipsing. That's why I use the word eclipsing here. Yes, sir. I am wrong, right or wrong?
Understood, sir. You were right.
Huh?
Sir, I understood what you were trying to say.
Okay. Okay. I'm talking about more eclipsing one. These are all not staggered one. When the hydrogens, when these hydrogens are coming before the another hydrogen. Okay. When this hydrogen is, for example, is if you have a Newman, when they are coming in an eclipse way, then only you should use these values. Okay, not for the staggered one. If there's a staggered one, there is no eclipsing factor there. Okay, they are away from each other. Only in case of Dutch butane, if it is 60 degree, then only you should use this 0.9 kilocalories. Okay, understood?
Sir, actually, I was asking that in staggered one, there is one stabilizing interaction also. That
Yeah,
bonding
yeah.
and anti-bonding.
Yeah, that stabilizes it to 0 kil. That's why I'm taking it as a ground state. Okay.
Okay, sir.
Okay, I'm taking
Excuse
it
me,
as a
sir.
reference. Okay, with that reference only, I'm calculating for other eclipsing interactions.
Okay, sir.
Yes.
Excuse me, sir.
Yes, sir.
Sir, in case of staggered form, sigma and sigma star interactions takes place, but that only implies that there won't be instability. How does it
Yes.
lead to stability of the overall molecule?
Yeah. 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 So that is the stability of the molecule. So the potential energy will not become more. Okay. So this is we are talking with respect to the potential energy. The potential energy of the staggered form, we consider that it is the ground state form or it is the stable conformer, and we consider them as more or less as the reference. And from there, how the molecule interactions becoming destabilizing, or I don't put the word destabilizing, but which needs more energy to turn around. Okay.
So it means stabilization due to no instability.
Yeah.
Basically, we are taking that as a reference.
Yes. Yes.
Okay. Okay, sir.
So means there we are taking the energy as the reference, and with respect to that we are counting the destabilization of
Yeah.
due to these
Yes.
eclipsing.
Yes. Yes. Yes, for sure.
Excuse me, sir.
Yeah.
Sir, is a doubt in the Gauss-butane interaction. If we are asked to find the energy difference between Gauss-butane and the staggered
Don't worry
form.
about the Gauss butane. When I take butane by itself, I will teach you completely Gauss butane. Don't worry. Huh?
Okay. Okay.
Okay. Right now, I want to introduce the term. Because tomorrow class we will take the butane. There I will introduce completely Gauss butane. Don't worry right now.
Okay, sir.
Okay. So I hope you guys sort of enjoyed the class, or it was a learned, right?
Yes, sir.
Learn
Yes,
stereochemistry
sir.
nicely.
Yes, sir.
Yes,
So
sir.
I will be happy if you guys all get full mark in stereochemistry. I don't want even one guy to get what happened. Oh. I don't want even one guy to get even a 1 mark less. Clear? Yes. Huh?
Yes, sir.
All of
Yes,
you
sir.
should get full marks. That's my aim. Huh?
Yes.
Stereochemistry. If you go and do it today, if you have time, and next class, if you have any doubts, please come back to me. I'm ready to help you out. If you need any special class or any one class extra, I can also do for it. No problem. Okay, I'm there to teach things. That is one. Now we are starting with confirmation. Confirmation till now it is good, right?
Yes, sir.
Yes.
Okay then. So then we will
Yes,
meet
sir.
you. Okay, then I will meet you on next class. That is on Monday, right?
Yes, sir.
Yes, sir.
Okay, okay then, guys. Have a lunch because you guys have missed your breakfast. Sorry for that. Have your lunch. Okay.
Thank you, sir.
Okay.
Thank
Thank
you.
you. Thank you. Thank you.
sir.
Thank you, sir.
Yes.
Thank you, sir.
Thank you, sir.